Also, if there's any exam issues, let me know about it because, so for many of you, this is like the first time you had, an exam with me and how I grade exams. So, like for example, and some things were kind of confusing because I could there's like several examples I could name, but one that stands out was like on problem number 3. There was some confusion if I was talking about the amplification in terms of voltage or power. So if you did it, if you assumed it was power, then that's fine. I took your answer as power. If you assumed it was voltage, that's fine. Because after I saw that, I could clearly see how there could be, some discrepancy of like what type of amplification I was talking about. Another thing that popped up was, what's the comment that popped up? Yeah, there were. Like on problem number 9, like what form of H, right? I was asking about, and I left it open. If you wanted to give it in terms of decibels, that was fine. If you want to do it in terms of convert that to the usual form of H, of course, that's fine. And there was a lot of confusion about problem number 4. That was, yeah, I mean, it was kind of funny grading problem number 4 because like the equations are like all over the place for most people. On this equation, on this problem right here, okay, so it's asking for an expression for I0, and as I previously mentioned, I'm not asking you guys to do the algebra, or really not, for a lot of these problems. In this case, I'm asking you guys to set up the problem that you would solve algebraically to get I0, okay? And so from what some people wrote down and all the things that they wrote down, I got the impression that they spent a lot of time on problem number 4, and it seemed like it was more than 5 minutes. And so for like problems like 4, all I expect you guys to do is just do KCL at every single node. There are like 3 nodes there. If you do KCL, you have 3 unknowns, 3 equations. That's all you needed, right? Also, because so we just finished that first 1/3 of our semester, and so this material will appear again on the final for those of you who want to take the final. So, are there any questions about any of the problems? Like, is there a question about number 4 for anyone?
Number 4 real quick.
Yeah, sure. Okay, so Okay, so that's number 4. And so the idea here is, how would you determine I0? So what you don't have to do KCL, but the key is on problems like this, just make sure you write down the equations that's required to solve the problem. Okay? And sometimes when you write down the equation, you introduce a new unknown. If you do, that means you have to come up with another equation, right? So once it's all said and done with, the number of unknowns that you have to equal the number of equations, right? So if we did KCL at every node, let's call this V minus and V plus as usual. So let's call this node A, B, and C. So for node A, we have V minus minus V1, and this over here was our V1, over R1 plus V minus minus V out over R2. That's one equation. For B, we have this right here. Now, we could write this as V plus or V minus. Okay, if you write it as V minus, then that's that new unknown we're introducing. If you write it as V plus, if we did it like that, we'd have to have another equation up here that took care of that and said that V plus equals V minus, right? If we chose to write it like that. If we just use that as V minus, it would have been fine. We would not need that. Okay. So KCL for this right here. Oops. And then for this one right here is I0. So if we have the positive sense that's going out that node, well, that's going to be opposite direction. So that's why that minus is there, right? So V for R2. Okay, and so this is the one we're looking for right here. But we've introduced this unknown, that V minus, and we also have an unknown in V0. Everything else is given in the problem, right? Oh, and because we have V plus here, we have to have that equation. So if we wrote it like that, V plus, we have 4 unknowns. That requires 4 equations, right? If that was a V minus, we just only need 3 equations. And remember, all your equations, they have to be independent of each other. They can sometimes look like each other, sometimes, right? But make sure they're independent of each other. And also, in some problems that you guys will experience, if you take an equation and you differentiate it, that counts as a totally different equation. Even though it came from the one equation, if I multiply that equation by some factor, it's really the same equation. But if I differentiated it, it's a totally different equation, and then you can count it as another type of equation to satisfy your unknowns. Or you could integrate it. Okay? If I integrated all these things, I would have a total of 6 equations if I had 6 unknowns, and I would handle it that way. I could have also, I didn't have to do KCL, I could have did voltage division right here, right? I could have said that V plus equals R3 over R3 plus R4 times V out. I could have did that. That could have been this equation, and I could have got rid of something like this equation, and I could just use those instead. It's fine. Either way you want to do it. Any other issues?
What's the amplitude at either the one on question A and the last one?
The amplitude?
At either cutoff frequency?
Yeah, so the amplitude at cutoff frequency, so for this was like for a band pass, right? So the shape is something like this, and here's like a 0, the max. Here is your 3 decibels down, and that's where the bandwidth is taken at that band. So this right here is just A0 over square root of 2. Or if you did your A0 in decibels, you could have said how many decibels that was minus 3 decibels. Either way is fine. And this right here is the bandwidth. So that value right here, that is the value at half the power, or square root of 2 of the frequency. I mean, divided by 1 over square root of 2. I mean, not the frequency, the amplitude. I don't remember a problem that everyone had a problem with. That was like really confusing. Oh, what about problems? Well, a lot of people didn't get to the bonus, okay? And that's understandable. You know, you're spending your time on the first few, and I tried to make the bonus a little more difficult than the others, but some may argue if they were difficult. But I saw a lot of people not get a lot of people who tried problem B1 did not get problem B1. So I think that was the issue. So you guys want me to go over it real quick? Sure. Okay. Also, if you find any mistakes in the grading, let me know too. Okay? Because sometimes you wrote down something and I didn't see it, like what you're trying to do, and or it didn't make sense to me or something. Okay, so we had a system like this, okay? And we were given the value of the resistance capacitance on the time constant. And we're given the amplitude, the gain right here, we were given that. So we were given this right here, we were given this, and we were given this right here, which was 4 U of t. Okay, so what this means right here, of course, is that it was 0 for a very long time, and then all of a sudden, at t equals 0, it jumped up to 4 volts and stayed there. Okay, so here's our Vn, here's t. Now, because it was 0 for a very long time, any charge in those capacitors had dissipated, drained off slowly. Okay, so totally at 0 state. Then it jumped up to 4 volts, and then it stayed there. Okay, and now we know for the output. Oh yeah, in some of these problems, you have to think kind of holistically at the problem, right? To try to see what's going on. So for the output, so just by looking at that, you know the output is A0 times A2. A2 is just what the capacitor is going to eventually get to from V1. So eventually, I mean there's some RC time constant, but eventually the voltage across the capacitor is going to be just be V1, which is this. Eventually it's going to be that. But that is being magnified by your gain. So we know that this is eventually is going to get to whatever the gain is times that V2. In this case is 50 times 4. So it's going to be 200 volts eventually. It's not going to get there immediately because of the time constant, right? So it exponentially gets there in time. So it's going to start off at 0 and gradually go up like this and eventually get there one day. Okay, so that's how it's going to behave. And then you're asked to write, you know, what is some voltage at some time, right? So when you write your equation for your V out, you know it's going to be like, you know, whatever your maximum voltage is, you know, this is your V max right here, whatever that is. And it's going to be some exponential, right? In this case, your value is growing in time, so you can write it like this. Okay. Now this is tau. Now of course, there's someone who actually, you know, did the whole thing and wrote out the differential equation and everything. Yeah. If you don't remember what that form is and you do the differential equation, you'll get there, and they got that problem right. But if you know how these things behave with the time constant, they'll behave something like this, right? And at t equals 0, when time is 0, it's e to the 0 power, and that's 1. So 1 minus 1 is 0, and that makes sense because at t equals 0, you're at 0. Now, as time goes to infinity, it's e to the negative infinity, which is 0. And 1 minus 0 is 1. So you just get V max. And of course, as t goes to infinity, it's V max. So you test your extremes to see if this, you know, if this is right, and it is. So, and any other finite value of that is some intermediate value. Now we're looking for t being 3 tau. Yeah, so that just means that at v of time 3 tau, we're going to be at 1 minus e to negative 3. And so, you know, here's like 1 tau right here, here's 2 tau, here's like 3 tau, and so on. Right, so we'd be like, you know, really close. And so what that means is that we're just getting closer and closer to the maximum value here. And so 3 of those, I mean, if you were looking at it like this, 3 of those is just 3 of these. And in class, we talked about what each one of these are, right? 0.37, 0.37, 0.37. Okay? So it's going to be a really small value. So you're like, you know, probably over 90% there by the time you get to 3 tau. And the shorter the RC time constant is, the faster it gets there, right? If it's like a really short time constant, it gets there really fast. And typically that's oftentimes what you want. You want something with a really fast time constant, meaning a very small capacitance or a very small voltage to get you there. I mean, resistance to get you there. Okay. All right. Any other big problems? Also this, if you got the wrong answer, but it took like multiple steps, and I saw that you made a step way in the beginning, I don't ding you for your wrong answer at the very end. I'll ding you for where you made your mistake. And then, as long as you use that mistake correctly, you won't get further dinged. And probably some of you see that happening. So, is there anything else?
You see from number 1?
Huh? Wait, what was that?
What's Vmax?
I didn't hear that.
What's Vmax?
Oh, for this case right here, Vmax would be this maximum value right here, which is 50. That's your gain times your 4 volts, so 200. Oh yeah, and in your problems, you know, because I was saying, you know, you don't have to do all the algebra most of the time. I mean, there are some times you need to do it, but most of the time you don't. But when you present your problem, you should always present your variables too, right? You know, so at the end of the problem, like someone was mentioning, you know, what is Vmax? So you need to write in there that Vmax is A0 times V2, and you write in what those values are, like in your problem, A0 equals 50. And the reason you want to do that is because sometimes the values that you have that's given to you in your in the wording in the text of your problem can actually be different than what you use in your problem. For example, like let's say A was given in terms of decibels or something, and the answer was supposed to be in volts, right? Or I don't know, some type of unitary type of transformation needs to be done as well, and you need to explain that. So as long as you plug in all your values, I mean, at the end you just write what these values are. You write what C is, write what that is. That's how you want to like really do it, okay? And if you do it that way, because that's exactly what you would plug into some computer software, right? Or your calculator to actually get it right, or Wolfram Alpha or whatever you use, right? Oh, you had a question?
Can you show us 1C?
1C. Okay, so for 1C, 1C, given a 6th order low pass filter, if the voltage gain is 79 decibels at cutoff frequency 13 kilohertz, then what would be the voltage gain at 243 hertz? Yeah, so this is like one of those bird's eye view kind of problems where you look at it and you like imagine what's going on. And I've seen people do this where I saw on the page where they had drawn the low pass filter, right? So they know it's going to look something like this and do like that. So here's going to be, you know, some cutoff frequency right here. This slope was 6th order, right? So that's pretty steep slope. And they know it's like a low pass filter. So the question is so what's given to you is this. So this is 13 kilohertz right here. And the question is what's going on at 243 kilohertz? Well, if that's 13K, that's going to be like way over here. I don't know, 243 hertz, right? And okay, so the gain was given to you at 79 decibels, right there, right? So the question is, if that's 79 decibels, then what is this at A? Because basically, this one is practically at A, or so close to it, you know. So if this one right here is 3 decibels down from that one, then that's just 3 decibels up from that one, right? So this is like one of those picture things, and a lot of times it really helps just to draw a picture, because so many people didn't draw the picture, but everyone who did draw the picture, they got the problem. Or some people maybe have done it in their head and saw it. But yeah, draw a picture and see what's going on. And then a lot of times you can just see from the picture, oh, it's so clear, it's this and this, right? That's why I made this to be really a really big difference between the values. Like this is a really high value. This was so far away, and it was low pass. You know, it had to be like basically at maximum at that value. Yeah, but that's the reason for the big difference between the two frequencies right there. Okay. Oh, I forgot my mic. Did you? Is it recording? Okay. All right. Okay, so we're going to use probably this material again in class going forward. So yeah, get all these concepts down, and also, like I said, for those of you who are going to take the final, the same types of concepts are going to be covered on the final. So if you want to do better than you actually did, you know, there's another chance, you know, to come back and do a really good job on the final. But of course, the final is very grueling. It's like 3 of these all in a row. Like 3 midterms in a row, so it's pretty grueling. All right, so for today, lecture 17. Okay, so for review, we went over the low pass, high pass, and band pass. We looked at what the frequencies were and the quality factors for each one of them, and the transfer functions. And these were like the peaking of the low pass, the high pass peaking, and also the band pass. We also looked at the switch capacitors too. We looked at magnitude scaling and frequency scaling. And then for lecture 16, we looked at this voltage switch capacitors, where we looked at this kind of system where this whole thing right here is like resistors, right? Where and also we can change this from being an inverting integrator to a non-inverting integrator by changing how we match up this switch with this one. Is it in phase or 180 degrees out of phase? Same here, right? So if this is like phi1 and that's phi1, or that's switch 1 and that's switch 1, then it is an inverting integrator, where that's negative. If we switch them around, where this is now switch 2 and that's switch 1, so this switch and those in this S1 are now in phase, and these two are now 180 degrees out of phase, then it becomes a non-inverting integrator, right? So that just means that if it's an inverting integrator, the current goes this direction. If it's not an inverting, then the current goes this direction. And you change the direction just by changing the phase of those with those. We also found out something else interesting too. Like here's an example of band pass. We can replace these large size resistors with these things, which are actually smaller when you fabricate them. Okay, and the resistance here, R2, is just this T over this is the switching period over C4, right? And you can see this right here. This piece right here is just like this thing right here. So this whole thing behaves like a resistor, and this behaves like the resistor right here. And if you do that, you see that we get our frequency here. But the nice thing about it is that one, you can get a very large. I didn't write the resistance. I'm sorry. But anyway, okay, so we get a very large size resistor here, value. But for the frequency, what happens is that you can control your frequency you control your cutoff frequency with your sampling rate, which is really nice. Here's the quality factor of that. We also looked at these digital to analog converters. This was weighted resistor. Here's a type of ladder. You can also do it with capacitors too. Here's the weighted capacitor version. Here's the ladder type of capacitor. Also, we look at an inverted ladder and also this non-monotonic DAC right here. And and what we mean by monotonic is like a curve that goes like this or this. That's monotonic, right? Like the slope can be constant, or the slope is constantly increasing, right? But if you have a curve where the slope, it can change like that, it's not like always increasing at the same rate, then that's non-monotonic, right? Of course, this is really, okay, so that's what that means. Yeah. So now we're going to start on analog to digital conversion. So this is the other way. Instead of digital to analog, now we're going to do analog to digital. Okay, so the analog to digital converter, it takes an unknown continuous analog input signal and converts it to an in-bit binary number that can be readily manipulated by a digital computer. So here's the block diagram of this. Here's the input, this Vx. It goes in here, has some reference voltage on this block, and outputs the binary numbers. Okay, and we'll look at different kind of forms today. So here's what the ideal case looks like. So here's the input voltage Vx, right? And remember what full scale means. Full scale is whatever this amplification factor, this gain factor is, times your V reference, and that's your full scale. Okay, so your voltage comes in at some proportion of this full scale, so it goes from 0 to full scale, right? So that's your input, and here's your output in terms of binary, okay? And so what happens, you have these quantized jumps in here, and we'll talk about how those happen. Now, this is also your input right here, but here's your quantization error. Okay, and so what can happen is that you don't have to be exactly at this value. You could be a little bit over this way or a little bit over that way and still get the right value. Okay, and in this case, it's like half of the least significant bit either way. So this whole thing is one least significant bit size. And this is like half of that. Okay, so there is some slack to play around with, and there is going to be some slack. Now, here's an example right here. So for a 3-bit system, is 2 to the 3rd power. That's 8. I'm sorry. This is wrong. This has 8 values right here. Okay, but it's a 3-bit system. I'll change that. So for example, this number right here, that would be 5. Or it'll be 5 over 8, because you have 8 possible values of your full range, your full scale voltage. And so this input Vx, it could range from 4.5 over 8 times this to 5.5 over 8 times that. Or you could put these in terms of fraction, that's 9/16, between 9/16 and 11/16. Okay, and here's your least significant bit right here. Is full scale over 8. Okay. Now here's some error types. There's a couple you can have. You have an error type right here where it's a non-ideal 3-bit analog to digital converter, where you can see at this point right here and this point, there's a little bit of slack right here before that bit changes from this value to that value, right? So that can happen. Also, you can have an error like this, where something is skipped. So you have some missing code. So you're supposed to have a data point right here, but it did get triggered until like you got this high value, then it jumped over here. So that can happen too. Okay, so here's some techniques. So most of the techniques, they involve this comparator. Okay, so what this comparator is, a voltage comparator compares the magnitudes of two voltage inputs and determines which is the largest of the two. Okay, so basically what happens is that it saturates. This is really steep right here, so it's going to saturate to this value or saturate to that value when it compares these two. And so this is what this is what it looks like, and that's why you have this sort of like infinite slope right here for the gain. Okay, so for this one right here, this is the most simple analog to digital converter, and it's a counting type of method. So what happens is your Vx comes in, and then this flip-flop is engaged in this, for to pass through this right here, you have this clock. So whenever this and this are the same value, then it starts counting like that. So the problem with this is that it has to actually count every single time up to your value. So it's the simplest one on there. The simplest one that we're going to look over, but it takes the longest amount of time because you're always counting. If it's a small value, you're fine, right? But if it's a really large value, you have to keep counting and counting and counting until you get there. So that's how that one works. For this one right here, it's called successive approximation. And this uses like a binary search method. So here's like this successive approximation logic that goes on here. So what it does is like, first what it does, here's like full scale from here to here. First it cuts it in half, right? And then it finds out what that value is. Is your input larger or less than half? If it is larger, then it cuts the next part in half, and then the next part in half. And it sort of like zeroes in using like a binary type of search to find it. And that's faster than the other one. And here's like an example of, first is here, but the actual value is higher than that, so it goes up to there. It's higher than that, so it goes up to there. It's lower than that, so it goes down to there. And that's how it finds the final value of whatever came in. If it was lower than that, it would take this path. Okay? And this is a single ramp method right here. And what this method uses is, this is like an analog ramp generator, and that's this piece. So the ramp here is used so there's a constant rate for that ramp, right? So a ramp is going up, and then it's sort of like counting how long it takes for that ramp to exceed the value of the input. Okay? If it's a low value, that time is small. If it's high value, it takes a little longer, right? So it's like this kind of ratio. Your input over your full scale divided by, is equal to the number you're looking at, or the number you're interested in divided by the full scale of the number of your binary bit system. Okay, so that's the one behind this called single ramp. There's also a double ramp we'll talk about next time. And for the last slide right here, this is the fastest one that's available. It's called Flash analog to digital converter. And so right here, you can see you have like this voltage division thing going on, right? Here's your reference, and then it's picking off these different values. They're all like a resistance apart, okay? And then you have all the comparators, but at each one is like picking off what it is. So you're delivering, your bits over to your combinational logic right here. And so it's the fastest one. It has like about a nanosecond kind of conversion time to go from input to output. And we'll talk about some others next time too. Okay, so see you guys on Friday.